get everything going. Okay, I'm very happy to introduce Nicolas Behr, who will talk about Tracelet Hopf algebras and decomposition spaces.
Thank you very much, and thank you also to the organizers for this effort, for this really interesting hybrid event. Hope maybe next year it'll be in person again. So I would like to emphasize this joint work with Joachim Kock, whom you know, I suppose, in this community very well. And I thought maybe a good start would be to just a little bit of a disambiguation. I mean, we have heard in this conference already a few talks and also in previous events about these sort of chemical reaction systems modeled as discrete transition systems. So the idea here being that sort of the semantics of these systems is you have some sort of tokens, maybe of different kinds, and then a chemical reaction at its very basic level is just a replacement of such token, or a firing, if you will, of a transition that consumes some tokens and produces some others. So the unfortunate story goes like that the moment you want to put more structure into your tokens themselves, if you will, actually, if you want to give up the idea of tokens, if you want to speak about manipulations of graphical structures, you unfortunately lose all of these very nice properties that Petri nets or like string diagram calculus and so on have. And this is very simply because this idea of just picking a token and then that's the only information you need is no longer valid. So in these graphical writing systems, the semantics is more like you try to find a sub-pattern in a larger structure. And then you want to manipulate this sub-pattern. And maybe you actually want to keep some of the vertices, like, for example, in the middle, you see like a transition, which is one of social network model, for example. And the most important thing is that in this triangle here, the extremities are, again, they're all chemistry, because of course it's a level of abstraction you're picking. But the important bit is that in biochemistry, but also in organic chemistry, sort of this type of idea of just replacing entire molecules is no longer the correct one if you look at the reaction systems you find in biological or chemical systems. Namely, the more correct abstraction level is that you locally manipulate some of these molecules that might bind or unbind or get modified. And so this makes for an extremely different semantics. And so the story of this talk is that, so what becomes of string diagrams? So in these more general categorical writing systems, I will show you, the carrier of causal information is so-called tracelets. So they generalized string diagrams. And these tracelets, so normally in string diagrams, the salient mathematical structure is symmetric monoidal categories. So in tracelet theory, the salient mathematical structure is a certain type of combinatorial Hopf algebra. And now the beauty of this collaboration with Joachim was that Joachim, of course, is a proponent of this very general mathematical theory of decomposition spaces. And we managed to figure out that actually tracelets do naturally form a decomposition space, which then explains why this particular type of Hopf algebra arises. Okay, and since I guess I already mentioned a lot of concepts that are not quite well known in this community, I thought it would be nice to start out from precisely the simplest possible example, namely this chemical reaction systems modeled as token replacement system, which is in this hierarchy, so to speak, discrete writing. I will explain briefly in this intuitive example where you can salute string diagram calculus, how Hopf algebras arise. And then, of course, I will switch to the general categorical writing story. Okay, so this whole idea of, why Hopf algebras, why should they be important to dynamical systems? So I actually found this not in dynamical systems literature, but when I was studying some combinatorics work by Paul Borchak and colleagues, where they were formalizing what's called the normal ordering problem in combinatorics. And so from this work about 5 years ago, I had a first attempt of doing graphical writing theory in some sort of relational calculus in joint work with Vincent Arnaud and colleagues. But anyway, so I will pick a particular aesthetic for my diagrams, which is inspired from a writing theory. So they look slightly different than string diagrams, but of course, I guess you could perfectly well draw them as some sort of hypergraphs or string diagrams. So the idea is, look at the very simplest possible writing system there is, just the creation and deletion of vertices from a pool, or from a discrete graph. And so the V-dagger diagram, so I'm drawing these diagrams because I will distinguish between sort of the vertices that act as an input to an operation and those as at an output, but I do not want to put colors on those. So I instead put these little wires. So the V-dagger motif is I create a vertex without asking for an input, and the V is I delete a vertex. And you will see in a moment, it's quite important to have sort of a little plaquette for these elementary moves, because they will be essential to this type of diagrams we will construct. And so a generic diagram in discrete writing theory looks like this. You have a bunch of vertices, some of them act as inputs, some as outputs to an operation. And in addition, I have these blue wires, and they are used to link some outputs to some inputs. And the rules of the semantics is that you should not link, so at most you can make one link per vertex, yes? So, and mathematically, this is just modeled as a set of output and input vertices, and as a binary relation that should be one-to-one or like a partial bijection. On top of that, since we want to have this semantics that a diagram is more, I mean, the positions are really not important where things are drawn, so you quotient by isomorphisms on the vertex sets, so such that, of course, keeping these incidents intact. And now here is a key idea which is typical in combinatorics, but I don't think it's very typical here in this community, because rarely do you ever want to reason about just one diagram. You want to typically more reason about entire families of such diagrams and their compositional properties. And so in the combinatorics literature, there's this beautiful idea of sort of doing a bookkeeping by, so here we have the set of equivalence classes of diagrams, that's our starting point. And now we endow this with a vector space structure. So basically we introduce a vector space curly D over some suitable field, let's say, for example, reals or complex numbers. And then each basis element is assigned to one such equivalence class, so that then this operation makes sense. So now we define what's called the diagrammatic composition in this particular lingo, where you compose two basis elements. So basically this right-hand side ranges over all ways. You can wire together the two diagrams that are underlying the basis elements. And the sum makes no sense because we are in a vector space. So you sum over all ways to wire. And this funny composition operation itself amounts to wiring, and so picking a wiring and then, you know, forgetting that these were coming from two different diagrams, and of course quotienting by the equivalence class. That gives you a well-defined operation. And first of all, this particular structure, now the vector space, which we got from, you know, basis vectors are tagged by equivalence classes of the structure we want these diagrams. Together with this operation, this gives you an associative unital algebra. And the unit element, the left-right unit, is of course the basis element assigned to the empty diagram. Okay, but there's more. So first of all, by simply looking at this, you can make a little zoology of sort of the sub-diagrams that can arise. Of course, we had like the elementary ones we started from, creation, deletion of vertices. And then sort of at larger, the next larger ones is this sort of E, called E in the literature, the position where you first create a vertex and immediately delete that afterwards. And then if you think about this for a moment, you see that any other diagram is just a disjoint union of copies of these three elementary ones, because simply my semantics doesn't allow for any other wirings. And disjoint union here can be emulated by composition of the diagrams along empty overlap and then quotienting. That happens to be exactly the disjoint union operation or monoidal product, or however you want to call this. Okay. But, and then, of course, the question arises, how can I elegantly express that all my diagrams actually look like this? And so there's this beautiful idea, and this is deeply motivated from quantum mechanics and from, you know, combinatorics and so forth. The idea is, well, if you look closely, these three elements here, so, I mean, actually they're associated basis vectors, together with an operation called the commutator, or actually it's like a Lie bracket. So the commutator is you compose A with B in this diagrammatic form and you subtract B compose A. And so this commutator somehow is an account of sort of elements that can only arise in one or the other order of composition typically. And so the only non-vanishing one on these three elements is the one where you first create and then delete, minus first delete, then create. So in one order, you can get this E element, in the other, you can't get this causally. And so indeed, the commutator gives back this relation. And now the high-level mathematics trick here to make an elegant statement of why are these three elements important for this algebra is the following. So you take the universal enveloping algebra of this Lie algebra, which is a fancy way of saying you take first the tensor algebra. So elements are sort of, if you want, words in the letters, which are these three elements. Modulo the ideal, and this is sort of here in the quotient, generated by this. This is the only commutator relation we have. And this is just a fancy way of saying, so the Poincare-Berkoff theorem says, if you give a preferred order on the basis elements, here traditionally we choose the creators all to the left, the B dagger, then the deletes, and then the E's. Then you're guaranteed to be able to bring any element into this normal ordered form, modulo by repeatedly applying this commutational relation. And so the theorem, the deep meaning of the theorem is that then really the basis of this algebra you get is given by these normal ordered terms. Now, if you know your mathematics in this field, first of all, it's immediately clear that either you say you have a preferred order which just lists the elements of the three types, or, I mean, before we just had disconnected components. So basically the data is the same whether you give it in this U algebra or whether you give it in the original diagram algebra. So there's an isomorphism. But the main point is that this universal enveloping algebra is known to be a Hopf algebra. And then you can ask, okay, so the composition structure was this diagram composition. What's the decomposition structure? And here it turns out this is, one classical example of a Hopf algebra where the coproduct is something that allows you to reason about the connected components of elements. So essentially the coproduct here is just you have an operation which takes a basis element and gives the sum over all ways you can partition into subdiagrams the connected components of your original diagram. And so indeed, this gives rise to this type of combinatorial Hopf algebra. And then the question is, what do you do with it? I mean, does this have any interesting computational meaning? And so looking again at, any diagram is some copies of these three elementary diagrams, you can see that you can interpret the composition of diagrams combinatorially. So what's happening here is I'm composing two such diagrams in the standard form. And the right-hand side ranges over all possible outcomes. So again, of course, I'm guaranteed by the Poincare-Berkoff theorem. My outcomes are again of the shape, like some copies of the elementary diagrams. And the only combinatorics here is the number of ways you can form R wirings, given my semantics, forgetting, of course, the order in which I form them. And you see that this directly enumerates all the possibilities you can get these composite diagrams. So that's the strength of this Hopf algebra approach. So back to the idea that somehow this was sort of the elementary level Hopf algebra for just this discrete rewriting case. This would be still doable in string diagrams. And then, of course, then the question, so how does this generalize to these more complex types of rewriting systems? Yes. And I should say that what's not in question, what's never in question, was that the way to the semantics for these rewriting systems is formulated is so-called categorical rewriting theory. And that's a research field that has been around for at least 50 years. Yes. The question was about how do you reason statically about the properties of such rewriting systems. So let me start out by just, double push-out rewriting, interestingly, has been mentioned a lot in this community over the last few years, it feels. And so you will have seen this before. So a double push-out rewriting step consists of, you have to specify as input data a writing rule, here drawn as a span on the top, OKI. Input, what you keep, what is the output. And typically we will use for O and I monos, but I didn't highlight this here especially. And then you choose an embedding of I into X with some monomorphism, M. Now, your underlying category is some sort of adhesive category. So you can ask, does exist a push-out complement? So, in set rewriting, this would be the set complement operation. In graphs, it's something slightly more complicated, but it's essentially asking, can you form a commutative square, which is push-out? If you can, then you take another push-out, and that's where the name comes from, double push-out. So this defines you one individual rewriting operation. And just to show you that this is not some abstract nonsense, I'm showing you here an example from one beautiful example from chemical writing theory, which is taken from the website of my collaborators, Daniel Merkel and Jakob Andersen of the algorithmic cheminformatics group in Odense. So you see here on the top, it's a little pattern transformation in a template in a molecule. And here is an actual chemical molecule. And here it turns out you can form the push-out complement and the push-out. And so this really codes for real life transformation systems. This is an actual chemical reaction. And I just would like to mention, so if you're interested in this categorical writing theory, and in particular in this chemical writing theory, have a look at our, we have online seminar about this, and the second talk in the series, and all of these are on our YouTube channel, is exactly a long talk about chemical rewriting systems, if you would like to have a look. Okay. But then sort of the, and I mean, this is not really meant too seriously, but I mean, in this community, often then sort of all of the talks introduce this double push-out writing, and then it's over as an adhesive category. But then it really stops there, and that is funny because the field has 50 years of developments, and really the story doesn't stop here. It's a bit like if you tell me an elephant is an animal which has 2 eyes, which certainly true, but I mean, so let me show you a little bit sort of the types of things that happen when you go deeper into writing theory. So, and for illustration, I'm going to sketch here a little bit. I'm trying to stick with this idea of, you know, showing things in a diagrammatic fashion, because I think it's a good intuition. And so at the bottom here, I'm drawing an input graph. So this is a rewriting system over undirected multigraphs. And then at the top, I'm drawing 5 steps of a transformation sequence, where the first 2 create an edge, the second one deletes an edge, and then you create another edge, and then you create an edge. And so the coloring of these sort of wires is that if I draw them in red when sort of the operation touches something which was already present in the original state, and I choose a blue coloring between these steps when you touch something that was used or produced or something like that in a previous step. And now here you exactly see why this is never going to be a string diagram. Because, so the type of thing I want to ask of these systems is, for example, can I produce a triangle with such a rewriting sequence? Now, if you think about it for a moment, this input state x0, certainly you can count how many triangles are already there. But this doesn't allow you to reconstruct the state. So somehow the state x0 certainly is not characterized unless you are in a very special type of graph by number of triangles. And so this is exactly the crux of the matter. So I'm asking pattern counts, but a pattern doesn't characterize foot my state. And that's a general story. In fact, if you think about how many isomorphism classes of graphs you would already have on this few number of vertices, that's a huge problem, because you would have to count each iso class as a type of token if you wanted to do this as a Petri net. So that's one kind of complication. But the deeper problem is that I want to be able to reason about the internal structure of these rewriting steps. I want to be able to say, for example, here, these steps colored in orange don't really contribute to this particular problem of creating a triangle, because they create an edge and then delete it again. So it's sort of a null around. And at a very deep level, it's really about the structure of these wiring diagrams themselves, because if you look closely, I mean, one could think maybe it's some sort of string diagram where I have to plug graphs into graphs in some shape. I mean, the wires might be carrying some graphs. But then you find that actually the semantics will tell you that sometimes you can touch an edge in a later step without touching each of its endpoints. And so also that idea fails. And that's actually quite a crucial point. I'll make this later when I introduce tracelets. But other than that, it'll be, so the idea is that these sort of wirings together of operations, which look remotely like some sort of diagrams, these actually will be what's called tracelet, and they are the causal carriers of information in these rewriting systems. All right, so the first order of business is to obtain actually this tracelet semantics. And so for this, you have to go to a slightly deeper level in writing theory. But again, this part, at least, this is still 30 years old, at least, a so-called concurrency theorem. The idea is if you do 2 rewriting steps, one here and call it in red, one in blue, we are doing this rewriting theory normally in some type of adhesive category. In particular, these categories satisfy the following property. So whenever you take a co-span of monics, then this factors uniquely up to universal iso through a jointly surjective co-span of monics followed by a mono. So this way I get the splitting here into this object J210. And then one can show that one property of these double push-out plaquettes is that you can split them vertically whenever you split one of the sides, so to speak. And so this gives you these 4 plaquettes. And now in the next step, you simply do, so remember these hook arrows are spans. So if I do span composition, I can produce this shape of diagram. And now the so-called synthesis part of the concurrency theorem says when you do the sequence, you start from sequence of 2, perform the splitting, perform the vertical splitting, compose spans, and then forget this upstairs part of the diagram. Now you have produced a 1-step rewrite from this two-step sequence in a uniform way, and that's called the synthesis construction of the concurrency theorem. Conversely, if you are given such a one-step sequence and you know it came from such a diagram above, where in particular the rule you use for the rewrite is the span composition of two such rules as up here, then you can uniquely up to universal isos, of course, reconstruct a rewriting sequence of length 2. So there's sort of this, it's equivalent to speak about all possible ways you can form these composite rules and apply them in one step to an object x0, or looking at all possible ways to get two-step sequences. So that's a very well-known theorem in rewriting theory. Most of concurrency theory on derivation trace on sequences of rewrite is based on this particular insight. But when I started, I'm a physicist originally by training, and 7 years ago, and I wanted to start, do combinatorics with these things. I realized that one needs also some guarantee on three-step sequences. In particular, you need to be able to sort of list all of these options. So the problem is you have a three-step sequence, and now you could use the concurrency theorem to, for example, split the first 2 bits into this shape. And then you can do it again to split on the third step. And so you produce overall the shape of diagram, and then you compose out and you get sort of a particular upstairs part, which is a sequence of 3 of particular properties. But I mean, that would only be useful if it didn't matter if I first analyzed the 3 with 2-step and then with 1. And it turns out, fortunately, this is the case. So up to universal isomorphisms, I could have obtained this this particular shape with this particular middle layer up to universal isomorphisms, also from analyzing in the other order. And that's what I call associativity. So that was my insight here, that you can, because he proves that at length 3, you can reconstruct sort of this upstairs bit. And by the way, this upstairs bit is what's called the tracelet of length 3. In this sense, these tracelets carry the minimal information stored in this derivation sequence as to how these rules interact. And so in that sense, tracelets are minimal. And it turns out that because at length 3 this works, you can inductively show that tracelet exists for arbitrary lengths. And so the way to define this is at length 1, you just pick rules. They, of course, are just trivially tracelets because, any such diagram on the right is a plaquette of 2 pushouts. At length 2, you perform exactly this thing. You search for jointly surjective Monte spans such that you can rewrite in double pushout fashion to the left. And then I'm just putting this dagger here to indicate that I'm going against the first rule to get the shape of diagram. Yes, it's completely symmetric definition. It's just to indicate how I obtained the diagram. And so this would give you all the possible traces of length 2. We are doing this for writing over finite objects, so there's finitely many of those up to ISO. And then at length 3, you take a trace of length 2, you take another rule, you find such a jointly surjective monic cospan, and then you try to do this DPO rewrite. If that's possible, then you compose vertically and you get a tracelet of length 3. And then, of course, you do induction and you get tracelets of arbitrary lengths. So, that's sort of one of the funny properties if you're doing DPO writing of adhesive category. And the first hint that this has something to do with these diagrammatics is that if you now take 2 tracelets of arbitrary finite length, so the one in red and one in blue, it turns out you can define a composition on them by, again, picking a jointly surjective multi-cospan from the output of one to the input of the next, and then trying to do these rewrites. If it's possible, the whole thing composes, and you can show that this is, again, a tracelet. So there is some notion of compositionality here. But now the key point is we wanted to be able to reason about the totality of all of these tracelets in some algebraic way. We want to be able to do counting and statistics and stuff like that. And now here really comes the meat of the matter. So the main point of the collaboration with Joachim. So when shortly before I presented tracelets at ACT 2019, I met Joachim and Ebra, and we had a discussion on the blackboard, and he was immediately, somehow this particular type of property somehow immediately motivated him to think, oh, this must be a decomposition space. And then we got to work this out at the beginning of the year, which led to this particular paper. So maybe quickly to say, I think decomposition spaces might be quite well known here, but just in case, so decomposition space is a simplicial groupoid, which is to say that of a particular type. So it's to say you have some grading on the elements of the groupoid. So with boldface x are the degrees, x1, x2, x3, and so on. In the group in the decomposition space, we are interested in the zeros position is just one object, so that's not very interesting. But then you have this collection of arrows, so these face maps, the D's, and the degeneracy map S. And the idea is somehow that the tracelets, I mean, they're quite, these decomposition spaces are quite ubiquitous in combinatorics, because the typical idea is that the face map somehow forgets structure. So somehow it's, for example, if you think about trees, it's quite easy to put a cut on a tree in order to get a collection of forests in general. It's not so easy to put together trees. It's a more complex combinatorial operation. And so this decomposition space has a very interesting viewpoint, usually in terms of computations. Anyways, but so the original idea was, okay, so we put in zeros, it's just some dummy object. In 1, we put the trace of length 1, in 2, the trace of length 2, in 3, the trace of length 3. But then the immediate problem was that somehow at length from 3 to 2, you need 4 different face maps that are of a type, a trace of length 3 gets mapped to one of length 2. And so, I mean, it's not easy to find these 4 because somehow if you have a length 3 trace that you can forget the first or last block, that certainly gives you the right type object. But for some reason, it doesn't give you the correct type. It's not easy to just leave out some structure and still get a tracelet. And so here really the key point, and this took us the longest to work out, was that actually with these equivalences, you see you exactly have 4 shaded region of the correct type. So 2 of the face maps just read out this, top blue and the yellow bits, and the other 2 read out actually the other 2 shaded regions, these curly faces. So that was the starting point of our construction. But then Joachim had a second very important insight, because this would, if we sort of use this idea as construction, then we would only be able to get something like a pseudo decomposition space, because these diagrams above are only up to universal isomorphism. And Joachim wanted to have something more strict. And so here goes the actual construction we ended up with. And this is, of course, described in detail in the paper also. So as I said, in position 0, we just put a dummy object. And then in position 1, we put on the one simply a concrete span. So not like isoclass, we put a concrete span, which is a rule. And so the D1 and D0 face maps, in this case, just map to the empty object, to this one object. The degeneracy map just inserts from the empty rule on a one simplex. So far, nothing very interesting. But then at degree 2, you get this sort of Harlequin type diagram. And the idea is that in the lingo of decomposition spaces, you say the short edges of this 2 simplex are the 0, 1 and the 1, 2 edges, and the long edge is the 0, 2. This comes from the idea that in this case, for example, you have a rule on 0, 1, a rule on 0, 2, and you see above this little sketch, we had this composition of rules through, a tracer of length 2 and then composing spans. And the new idea is here, so the tracelet are the push out and push out complement things here, the red and green diamonds. And the blue thing is a choice of pullback that allows you to perform this composition. And now the idea is that the face maps, so basically the D2 face map, for example, deletes the vertex 2 in this 2 simplex. So you get back the 0, 1. So this reads out the first rule. The D0 face map reads out the second rule. But the middle face map, the D1, reads out the rule on the 0, 2, 1 simplex on the bottom. And that is exactly the composite rule. And so in this way, this setup allows you to compose rules sort of by applying face maps. And that is exactly the philosophy of Joachim in his general work on decomposition spaces. And so, I mean, there was one quick observation here. Sometimes these decomposition spaces come, for example, there's a version of such where you just have the path space of a category where you just, you put morphisms on the legs, on the 0 simplices, and then the long edge would be the actual composition of the morphisms. So this is not the case here, because the data of a 2 simplex is more than just the data of which rules are on the edges. So because you have these choices of internal diagrams here. Anyways, so how do we get to a decomposition space from this? So the next level is that you pick a 0, 1, 2 simplex that codes for composition of 2 rules. Now you put this composite rule as one of the short edges of another 2 simplex of the 0, 2, 3 here at the bottom. And then you pick a third rule and you compose out. And so the 0, 3 edge stores exactly the composite of 3 rules. And if you look at this now more closely, you recover exactly what, I mean, I don't expect you to remember this from the start of the talk, but I mean, if you want to scroll back later, if you see the recording maybe, you see that exactly this bottom piece codes for an instance where I can apply the concurrency theorem. So it turns out, so this composite rule and then its rewrite sequence, you can decompose it into 2 steps, which allow you overall to get inside of this tetrahedron here. And so the funny bit is that, and this is just possible by performing some push-outs. Yes, it's one of these, this concurrency theorem. Anyway, so you get this new object Z inside of the tetrahedron, plus already some objects on the previously empty front-facing 2 simplex. And then performing some further pullbacks and push-outs, you can show that you can fill both of the previously empty faces plus the interior of that thing with the structure needed, so that now the previously empty faces now code for the composition of 3 with the third with the second rule, and of that composite with the first. And so this is exactly a manifestation of this associativity property I was alluding to previously. And now if you leave out some structure from this tetrahedron, you can show that on the inside sits precisely a tracelet of length 3. And I've also highlighted the pullbacks you need to perform composition of the rules at the foot. And I should say there's an Easter egg hidden in our pre-proceedings. If you click on any of the diagrams in the paper, you get to an online version of these, and you can rotate, zoom in and stuff to inspect them in more detail. But anyways, yeah, and so exactly this property that up to universal isomorphism, you can uniquely produce from just the sticking of 2 simplices, this tetrahedron. This is precisely the axiom of a decomposition, or one of the axioms of a decomposition space. So more formally saying that this is a homotopy pullback, and homotopy because all of these reconstructions are up to universal isomorphisms. And so the central theorem of this paper, besides the Hopf algebra story, is that actually tracelets in this sense form a decomposition space. Okay, and so the final piece of the story is that going back to this diagrammatic idea, we wanted to be able to understand if things are not connected, they should somehow be commutative. I mean, that was the main idea of these diagrammatic approaches. And so for tracelets, I developed this sort of normal form equivalence already in the original version of tracelets. One part of the equivalence just takes care of not distinguishing between tracelets that are linked by isomorphisms. I also wanted, for technical reasons, not to consider when there's trivial rules in the tracelets. But the important bit is that there's something from the writing theory again, which is called shift equivalence, which allows you to reason when 2 blocks or more blocks can actually be commuted because they don't interact. And so that there's a particular special case when you compose 2 tracelets along completely empty intersection. This exactly up to this equivalence then emulates the disjoint union. And now, so now the rest is really just following the recipe. Primitive tracelets are such that are not empty and cannot be written as disjoint union of 2. Then you make a vector space over primitive tracelets. You define composition as, again, like the tracelet composition, sum over all possible ways to compose. Tracelet decomposition, so decomposition in connected components, is exactly giving you rise to the co-product structure. This fits nicely together, given by algebra. And also there's this filtration structure. Whenever you compose, at best you get the sum of the number of connected components, or you decrease because you wire up some parts, essentially. And this then very nicely fits into general mathematical theory to say this is actually then a Hopf algebra, which happens to be the universal enveloping algebra of the Tracelet Lie algebra. So basically the algebra of primitive tracelets modulo Lie bracket. Okay. And so do I get 2 more minutes? Is that possible? I think we started a bit later.
Yeah, no, you have more time than this. You have probably 5 minutes, including questions.
Oh, that's fantastic. Very, very good. Yeah, because I didn't want to leave you with sort of, which, I mean, I should say, so I enjoyed very much working with Joachim on these formal aspects, because, I mean, it's just like I really like decomposition space, and it's nice to see we can now do this in categorical writing theory. But I didn't want to leave you without at least one application. And this is from a paper I wrote last year, which is also available online. And the idea is, look now, so what can we learn from Hopf algebra? So the point is, here I'm looking at a problem in combinatorics. It's a uniform generation of planar rooted binary tree via the Remy generator. And the Remy generator is an ingenious idea. So everybody knows that, for example, if you have 100 vertices and you want to get a random tree on it, there's 10 to the 217 possible isomorphism classes, so it's difficult to pick. But there's this ingenious idea to randomly sample by simply applying 100 times this generator, where in each step you pick an edge, and then you either, and you delete it, but you keep the endpoints, and then you insert this Y shape, and you either insert it in the left or right fashion here. And you do this 100 times in each step, choosing at random an edge and which one to go. And this is guaranteed to give you a random sample, uniform sample from on some of all planar rooted binary trees. So that's the Remy generator. Now, if you think about this from rewriting, what we will do now is we will look at how such a rewrite step produces or deletes edges for sake of simplicity. So sometimes an edge was already there and you applied the generator and then nothing, you didn't modify anything. And that's, for example, the case for these positions where you have these identically preserved vertices. But sometimes you touch an edge which you have only available after applying the generator. And there's actually 3 ways to do so. And on the other hand, if you first try to find an edge and then apply the generator, again, there are some situations where you do not modify anything by applying the generator. But here, for example, this edge you consume through the generator. Now, what the Hopf algebra allows you to do is to really subtract all of these options. So if the counting of edges is modeled by an identity rule on an edge, and then the other things of just composition, and you see, for example, you can immediately discard all of these options that didn't actually interact non-trivially in a sense with this generator. And so it allows you to do a statistic accounting on how many ways you have new after applying the generator minus which option you lose before by applying the generator. And there's some sort of counting statistics. And now, not to say that, so if you, this is impossible to visualize easily, but I mean, now you take larger patterns, not just edges, but say Y shape, 2-legged left trees, 3-legged left trees, and so on. And now, I mean, I'm not going to run through this in detail, but the point is you can, again, perform precisely this type of analysis. And you get so-called commutator relations. Yeah. So you get G hat is storing the terms, the sum over the possible contribution of the Remy generator, and the O hat will count these patterns, the Hopf algebra elements associated to the identity roots. And this gives a sort of weird-looking commutator closure. And I refer you to the paper for the details. But then it turns out that through some stochastic mechanics stuff, you can, from this, get to a statement that these 4 observables are closed in a certain sense. So, I mean, every tree has the same number of a certain number of vertices happens to have the same number of edges and Y shapes, but the other 2 things are non-trivially distributed. And I'm drawing you here the full probability distribution, the joint probability distribution of accounting the 2- and 3-legged left trees. And you see, I can draw you this even at this ensemble of 10 to the 217 base points. I can draw you the analytic solution. And strangely enough, sort of ironically, this is now as if this was a rewriting system just on the numbers of these patterns. Yes. So I've sort of done a discrete bias simulation. We can discuss more if you're interested, of course, offline. Anyways, so the outlook here is that, of course, we ultimately want to use this for Markov chain theory. So that's what's the whole motivation. And also there's a question of tool support, and I'm currently working with Reiko Heckel on this package called ReSMT, which is trying to hack this problem of composing tracelets. And of course, then, because already we are finding some examples of combinatorics, that it seems to be like a natural arena to start from, not quite as complicated as Markov chains. And okay, and so I would like to close with extending an invitation. So certainly we can use more applied category theorists in categorical writing theory, and we now have the seminar series, so you're more than welcome to join us for some of these events. We are a very open and friendly bunch as well. And I would like to say that I'm going to start a working group on applied category theory related questions in writing theory this fall. And if you're interested to participate or contribute even, then please do get in touch. And for example, recently I learned from Richard Garner and my collaborators, Norm Zellweger and Paul André Méliès, that you can also look at writing theory from a point of Grothendieck vibrations. And so naturally, one would like to discuss these sort of mathematics together and with the application in mind, this rewriting theory. So again, like if you're interested, please do get in touch. And the elephant in the room is, of course, ultimately we want to learn something about the behavior of chemical reaction systems. And yeah, so there's a lot of work to do. With that, I would like to thank you for your interest.
Hey, thanks.
questions.
Do we have questions for Nicolas? This, in theory, falls to me, but I didn't have enough hours sleep to ask a coherent question. No questions? Oh, Constantine.
Do you hear me?
Yes.
Right. So I got a bit confused on so these rewriting rules. These act on graphs.
Yes.
Am I supposed to think of the Hopf algebra acting on? So what is the category of modules over this Hopf algebra?
Oh, you then, of course, you assign then matrices to each Hopf algebra element, which act as endomorphisms on the vector space indexed by objects of your base space. So, for example, you would then basically you define a Hopf algebra element acts on an element on an object in the category as a sum over all ways you can apply it through choosing of a match. And that is then guaranteed to be a representation of this Hopf algebra. I mean, of the algebra part of the Hopf algebra. If that makes sense.
Right. So that's where I got confused. So this. And
I didn't show this. Sorry, just to say. Yeah.
This analysis part that is the co-algebra part of the Hopf algebra, or is it the Tanaka reconstruction of the module?
That's a good question. No, I mean the analysis. So synthesis and analysis have to do with sort of this. Sorry, can I show this? I think so. So synthesis and analysis have to do with the way this is internally compatible. So you can see that sort of the synthesis and analysis take care that this composition of steps is associative. Yes. So this is really the internal structure of the Hopf algebra itself hinges on this. What's called the analysis part. Yes. So you see that here, the reason I can glue together two simplicities and reconstruct three simplicities, comes precisely from this concurrency theorem, because it allows you to get inside of the tetrahedron, so to speak. So it's independent of the module structure. So does that make sense?
So, exactly. Okay. So now I'm getting it, but I'm missing a picture like that, like what you're showing, for the action on a module.
You're absolutely right. And I mean, the picture would look more like something you would basically have to lift this thing to a cylinder. So basically you would put at the bottom of the triangle, so the very input of this guy is I03. So you put a monomorphism into some object, and then you could basically produce sort of a filling of this, I mean, how do you call this, like a triangular cylinder, which would then be the action of that thing, if that makes sense. I mean, I should draw it maybe in the tea break or something. Yes.
Okay.
Very good question. Yeah. Thank you.
Okay, we should move on. So let's all unmute and thank Nicolas. Okay, Antonin, are you ready?
I think I am.
Sharing slides.
Yeah.
Okay, so next up we have Antonin Delpeuch, who will explain to us why the word problem for braided monoidal categories is unknot-hard.
Thanks, Jules. So yes, I'm going to tell you a story about knots and about braided monoidal categories. And because this is the Applied Category Theory Conference, I really want to convince you that this is actually super important for a lot of applications of category theory. So what is my motivation to work on this? Many of you might have heard of or even used these proof assistants that are available for higher categories. And if you've tried using them a bit to prove stuff, you might have sometimes realized that this is quite long and you end up spending a lot of time just moving things around. Like, so this is a sample proof where I'm proving something in linear logic. And although I do apply sometimes axioms that I've input in my signature, a lot of steps are just moving things around. And it's quite natural to ask whether we could automate some of this, because it'd be very convenient. And of course, these things deal with some notions of hierarchies. So the general problem of automating isotopy in these things is very daunting, to me at least. But we can look at simpler cases than the full theory. So throughout my PhD, I have been working on simpler cases of this problem. So I've been looking at various cells of this table that you might be familiar with. So it basically shows how these notions of hierarchy simplify in low dimensions. And today I want to tell you about braided monoidal categories, which are in this third column, third row in the table. And basically that's where it gets really interesting. And that's where the topology already gives you very interesting combinatorics. So that's the motivation. And now onto the actual problem. So what is a braided monoidal category? And it's simply a category that is monoidal and has a braid. So braid is just like a swap, except that it's not equal to its inverse. So that's why we draw two different string diagrams for the braid and its inverse. And the overcrossing or undercrossing tells you which one we're drawing. And then, of course, these things will satisfy some axioms. So this is the hexagon equation, and which I will not describe because I think the picture is worth 1,000 words. And then you have a few other equations. So just the fact that the braid is an iso means that the braid and its inverse cancel like this. And then finally, you have the pull-through move, meaning that you can pull any morphism through a braid or a series of braids which have consistent orientation here. So that's the full equational theory of braided monoidal categories. And so the problem I've been looking at is called the word problem for braided monoidal categories. So it's very simple. You give me two string diagrams in braided monoidal categories, and I need to determine if they are equal, if they represent the same morphisms, simply by applying some axioms of braided monoidal categories. So here you've got an example of this problem. We have two diagrams, and in this case, they are indeed representing the same morphism. So how do you do that? You first pull this generator here on the left-hand side through the braid here, and then that will generate another braid up here, which you can then simplify with this one. So even for such a simple equality here, you already have two axioms that you apply. Let me give you a few more examples of this problem just to build up a bit of intuition about the combinatorics here. So are these two diagrams equal? You can convince you that they are not, because, for instance, if you consider the left leg of the generator at the top in the left-hand side, it is connected to the left leg of this generator here, and that's not the case here, right? So this left leg is now connected to the boundary. And you can convince yourself that this sort of connectedness property, the connectivity of the diagram, is preserved by all these axioms in braided monoidal categories. So that's a way to show that these are not equal, okay? What about these two on the right-hand side? Well, it's tempting to think that maybe we could untwist this to get the equality to hold, but in fact, we don't have any axiom relating generators and braids. So you cannot untwist this left-hand side to get the right-hand side. So that's, again, not equal. And then you can come up with really all sorts of complicated examples like this. So here you could want to try to pull the generators in the middle on the left-hand side through here to get the right-hand side. But the problem is that the orientations of the braids here are mismatching, so you cannot actually do that. So again, here they will be different. And basically, I have absolutely no clue what sort of algorithm to use to determine if these things are equal or not. I think the third example gives you a bit of a sense that basically these things can be knotted. And if you want to solve this problem, you basically need a way to unknot things. So because I didn't have any idea how to solve this word problem, I tried to instead show that it is hard. And in complexity theory, we do this by reducing a known hard problem to the problem at hand. And of course, the natural choice in this case was to reduce the unknotting problem. So the unknotting problem is a very old and well-studied problem in knot theory, where you have a knot, which is the embedding of a loop in 3D, which is well behaved in some ways that I will spare you the details of. And then you have a notion of 3D isotopy, which is again complicated if you want to state it properly, but you can have a very good intuition of what it should be. And then the question is your knot isotopic to the trivial embedding of a loop in 3D? So this problem has been extremely well studied, and we still don't have any polynomial time algorithm for it. We know that it is in NP and co-NP. And recently there's been some advances also to get some quasi-polynomial time algorithms for it, but still no p-time algorithm for it. So to relate that to our word problem for braided monoidal categories, of course, we want to state it in terms of string diagrams. And to do that, the problem we have is that these pictures of knots involve some caps and cups. And that's not part of the theory of braided monoidal categories. So we need to add them. And then, of course, we need to add some axioms about them. So we need the yanking moves, which let you simplify caps and cups like this. And then we need the Reidemeister type 1 moves, which relate the braid to the caps and cups. So to summarize, you have some equational theory for braided monoidal categories, and on top of that, you need to add extra equations for knots. So that's a bit of a mismatch between the equational theories of both problems. So our result is that actually you can do this reduction. So you can polynomially reduce the unknotting problem to the word problem for braided monoidal categories. And that's not super surprising if you have this intuition that the word problem for braided monoidal categories needs to untie things. But it's still non-trivial because of this mismatch between the equational theories. Okay, so how do we actually do this? Let's try on an example. So you give me a knot like this, and I need to translate it to a braided word problem whose result is the same thing as whether this knot is knotted or not. So because I have caps and cups involved, I can try just replacing them by generators which have the same numbers of inputs and outputs. And now that's a valid braided string diagram, and then I can ask this question here. Now the problem is this is really not going to work because on the left-hand side you have 6 generators. On the right hand side, you have 2. And so that's something that's preserved by the braided axioms. And so there's no chances this equality can hold. So in fact, we can even come up with a stronger invariant, a bit finer. So if you orient your knot, you pick an orientation arbitrarily, and then you follow the strand through the knot, and you record which caps and cups you encounter and in which direction you travel through them. So first here I encounter a cap and I travel to the left, and then a cup, I still travel to the left, and then a cap traveling to the right, and so on. So that gives you a cycle of oriented caps and cups. And that's again an invariant up to braided isomorphism. And we actually have a second invariant, which is very well known in knot theory, and it's called the writhe of an oriented knot. And you get it by just computing local writhe for each crossing, which depends on the orientation of the crossing and the orientation of the strands involved. And you can check that this is also preserved by braided axioms. So let's go back to our example. You have your knot, you orient it, and you can propagate the orientation to all of the crossings. And then you look up the writhe for each crossing. That gives you +4 -2, so you have a writhe of +2. And now the really amazing thing is that given any picture of a knot, you can so compute the writhe, compute the cap-cup cycle, and you will always be able to actually construct a picture of the knot, which has the same writhe and the same cap-cup cycle. And then the crucial thing to observe is that if your knot is unknotted, then it will be equivalent via braided axioms to this picture you came up with on the right-hand side. So that gives us the reduction. Basically, given any knot, you compute writhe cap-cup cycle, you construct this funny unknotted picture on the right, and that gives you the braided word problem you need to do the reduction. So that's it. We have reduced the word problem for braided model categories and the unknotting problem. So we know that our word problem is at least as hard as this unknotting problem. Now, the really puzzling thing for me is that I don't even know if this word problem is decidable in the first place. So I'm not even aware of a naive algorithm for it, even though I think it really ought to exist. So if you have any intuition about this, I'm really keen to hear about that. And in fact, I'm also keen to hear about any other questions because I will stop here. Thank you.
Okay, thanks. Questions for Antonin?
Hi, Antonin. Thank you for the nice talk. Really pretty diagrams. I'd just like to ask, so recently this year, there was a result by Mark Lackenby showing that unknotting can be solved in quasi-polynomial time. Have you thought about how this interacts with your work?
Yes, indeed. So it was pretty bad news for me because the more algorithms you give for the unknotting problem, the weaker my result becomes in a sense, because I'm using the unknotting problem as a hard problem. So I was sort of disappointed, of course, but I think it's amazing that he pulled that out. Yes, that's basically the interaction between the two results. In general, I really struggle trying to translate any approaches to the unknotting problem to the general braided word problem, because it feels really, really different. But I know really little about all this theory, so maybe I should just read up more about it.
Thank you.
Okay, Paolo?
Yeah, thank you. Very nice talk. I have a question just about my understanding, basically. So when you added these cups and caps, you also added these axioms, these are Redmaster moves that basically allow you to twist the cap, right?
Yes.
So, but slightly before you were saying that when two wires enter a generator, they kind of keep track on which direction they come into it. So maybe I haven't understood exactly in which way you have to keep track of the direction they enter the generator.
Right. So you mean when we do this?
Yes, for example.
So that's still compatible with the Reidemeister type 1 moves because they can actually also preserve the orientation. So basically, when you apply a Reidemeister move, you swap the orientation of the cap or the cap involved.
I see.
I have not a slide at hand to show that, but if you look in the paper, there's also the diagrams for that.
Okay, I see. Maybe I'll look in the paper. Thanks a lot.
We have another audience question.
Hi, yeah, so sort of related to that, I was sort of thinking the same sort of question. I mean, are you somehow implicitly using frame knots here? I mean, is there some framing supposed to be going on, especially when you're preserving the ride? I couldn't quite.
Yes, so that's the idea, that all of these generators are in a sense framed because they can't be twisted at all. In the proof of the results, I use a different presentation of knots, which is called bridge form of knots. And that's, yeah, the tool that they use to eliminate the cup eliminations, also to get rid of the yanking moves. But yeah, this is really the crucial difference between these braided diagrams and the knots, because you have a lot of restrictions anytime you use a generator. It's very rigid.
Thank you.
Okay, we have another Cambridge question.
So in some areas of computer science, the fact that a problem is NP is sort of doesn't hold people back from actually producing things that work well in practice. Are there such things for this problem? I mean, things that try and decide equivalence and you know, are not guaranteed to always be correct, but work in practice pretty well.
I looked for such algorithms, but I really didn't find anything. I think it's still very early stage on all of the computational approaches to string diagrams. So I would really welcome that sort of heuristics. And I think it is probably very doable. But we really need to build up all the tools for that, and even just the interest in the field for that sort of thing to happen, I would say.
Thanks.
So I just have more of a quick comment, which is that for me, this is actually quite surprising, because I think that the naive guess would be that isotopy of braided monoidal category diagrams should be easier than not isotopy, because you don't have to worry about the Reidemeister moves, which can create and destroy braidings. You don't have to worry about the snake equations, which can create and destroy cups and caps. So going into this project, I mean, my assumption was in fact that braided monoidal. So Antonin and I went into this with, so one-dimensional, deciding if one-dimensional string diagrams are isomorphic is trivial. So we say we do that in linear time. And we have an earlier result that says that isotopy of two-dimensional string diagrams, planar monoidal diagrams, you can do in quadratic time. So when we started this project, I went in pretty confident that isotopy of braided monoidal diagrams would be in cubic time, right? because it does feel to me that there's no way it can be harder than not isotopy. But now this result is actually the opposite result. It's at least as hard as not isotopy. So to that, it means still, I think the original motivation that it should be easier than not isotopy still holds, but then the conclusion must be that it's just as hard as not isotopy, which is still a bit disappointing to me, to be honest. And I'm still, to be honest, fundamentally a bit confused as to why this isotopy of mere braided monoidal category diagrams is so difficult. But so I guess I'm saying this is actually quite surprising. It's not, I don't think it's the obvious thing that you would have guessed. It wasn't the obvious thing that we guessed, or at least me.
Okay, we should move on. There's a question in the chat, but Antonin, maybe you can just answer that in the chat. Sure. So let's unmute and thank Antonin. Okay, Zoltan?
Yeah, I'm here. I'm trying to share my screen at the moment. Oh, that's one way of doing it. Can people hear me and can people see my screen?
Yeah.
Okay, the same goes for the online participants. I'm going to assume that they can hear me too from here on. So it's a pleasure to be here. My name is Zoltan. I work for the Commonwealth Scientific and Industrial Research Organization. That's a mouthful. It's a national lab here in Australia. And today I'll be talking about my work on Treewidth in what we now call spined categories. And all of this is joint work with Ben Bumpus, who is at the University of Glasgow. And this will be a pre-recorded talk, assuming everything goes as planned, just because time is short and I don't want to run out of time. So let's hope this works. Let's see if you'll be able to hear me. I won't be able to monitor the chat directly, so if the chair can interrupt me if there's any questions, so I can stop the video and answer them, that would be fantastic.
Yeah, we have in previous days encountered technical problems with people trying to share video over Zoom, so let's see how this goes.
If there's technical problems, let me know, and I'll just do it myself. I'll just deliver the talk normally, but it would be better if it worked. So let me mute myself and let's see how things go. So we have Treewidth, which is can people hear that?
Yep.
Yeah, okay, fantastic. Let's get going. Extremely useful numerical invariant. It's a number associated to graphs. And normally I'd start by trying to convince you that this is a useful notion and you should care. But it happens to be so useful that we have encountered it twice already in this conference. First in Nihil's talk, and then in Tomáš's talk. But it has more broad uses and applications as well. Many NP-complete problems actually become easy to solve once we restrict our attention to graphs of bounded Treewidth. So when we start studying a new category of combinatorial or graph theoretic objects, it's often a good idea to try and find a corresponding notion of Treewidth. And very frequently, this turns out to be possible, but it's an ad hoc process, coming up with a new notion of Treewidth that works for your structure. Instead, what we wanted was a categorical description, capturing at least some of the meanings of Treewidth, and a uniform categorical construction of the actual Treewidth, so that whenever I start to investigate a new category of combinatorial objects, I can just apply this one construction and get a good notion of Treewidth immediately. And to solve this problem, we introduce what we call spined categories. And these are regular ordered categories, but they come equipped with some extra structure that will allow us to define Treewidth as a kind of functor preserving that structure. The category of graphs will constitute an example of a spined category, as will the category of hypergraphs. And most importantly, many lattices, including the poset of natural numbers. And this will turn out to be very important because this will be the category that acts as the codomain of our Treewidth functor. And once we introduce these spined categories, our main result becomes a sort of dichotomy theorem. Spined categories turn out to be either maximally bad, in that there are no spined functors from C to the poset of natural numbers at all. Or, if they're not maximally bad, then they are in fact very good, in that there is a best functor, which we're going to characterize later, this delta, mapping C to nat. And this best functor turns out to behave exactly like you'd want Treewidth to behave. Indeed, it coincides with Treewidth if C is the category of graphs, and it coincides with hypergraph Treewidth and the category of hypergraphs, and so on. So, before I explain how these spined categories work, let me give you a bit of intuition, just a bit, for Treewidth itself. And to do that, I'm going to start with a warning. When I say graph in this talk, I'm going to mean finite graphs that are not reflexive, edges are not directed, and there are no parallel edges starting and ending at the same node. Anyway, I'm going to take such graphs, and I will associate a number, TW of G, the Treewidth of G, describing such graphs. And this number is meant to capture how tree-like the global structure of the graph is. How close the global structure of the graph is to being a structure of a tree. Accordingly, trees themselves will have Treewidth 2. And the higher this number, the Treewidth, the less tree-like the global structure is. Let's see an example. This is a tree, but if I take this tree and blow it up just a bit, like that, it does not remain a tree anymore. Locally, when I zoom in, I see all kinds of cycles, loops, so on, completely inconsistent with being a tree. But when I zoom out and look at only the big picture, like that, this graph still pretty much has the structure of a tree. And in accordance with that, it indeed has Treewidth 5, which is low Treewidth. Now you can compare that to a complete graph on 37 vertices. The previous graph had 37 vertices. This graph also has 37 vertices. But this one has high Treewidth. It doesn't look like a tree at all. Not locally, not globally. So I hope I convinced you that low and high Treewidth are meaningful distinctions. So I'm not going to give you a formal definition of Treewidth, simply because it would take too long. It's not difficult, it just takes long. But I will tell you one important fact which served as the starting point of our work. You see, gluing graphs together along a common subgraph doesn't change Treewidth. It cannot increase it. Particularly, the Treewidth of the glued graph below is the maximum of the Treewidth of the blue graph and the Treewidth of the red graph above. This turns out to generally be the case. And as I think Sophie explained in her talk on Tuesday, such gluings are, from a perspective of category theory, push-outs. And interestingly, if you look at the right-hand side of this equation, taking maxima in the poset of natural numbers, or suprema in lattices in general, it's also push-outs. So we get this identity, and it suggests that perhaps Treewidth should be some kind of push-out preserving functor from the category of graphs to the poset of natural numbers. This is a great idea. There's just one issue with it. Treewidth cannot be a functor because there is a graph homomorphism from the 4 cycle, this graph here, to the edge graph or 2 cycle, depicted here. But this edge, it's a tree. And this cycle isn't a tree. The edge has Treewidth 2, since it's a tree. And the 4 cycle has Treewidth more than 2, since it's not. So the required inequality simply cannot hold. Okay, well, you say, but this issue has a rather obvious solution. Arbitrary homomorphisms do not preserve Treewidth, but monomorphisms certainly do. If G is a subgraph of H, then the Treewidth of G is less than or equal to the Treewidth of H. So we think we just pass to the category of graphs and monomorphisms, graph M. Objects are graphs, morphisms are monomorphisms of graphs. And we'll just characterize Treewidth as some kind of push-out preserving functor from this category graph M to the poset of natural numbers. And yeah, it doesn't quite work like that. You see, the problem is that the category graph M does not have push-outs, does not have enough push-outs. For example, the mediating morphism of this diagram is not a monomorphism. It's not a monomorphism because this graph has 3 vertices and K2, the edge graph, has only 2 vertices. So there cannot be a monomorphism between them. So the way we solve this issue is by axiomatizing what this category of graphs and monomorphisms remembers about the existence of push-outs in graph. And there is something that it remembers. This resulting notion, which we call proxy push-outs, is the major ingredient of the definition of spined category. Now there's also a minor ingredient, a combinatorial ingredient, and that's gonna be a sequence of objects, omega n, which is gonna axiomatize what it means to be a complete object, like a complete graph that we've seen before. So finally, we get to see that definition that I've been talking about all along. So spined category is going to be a category with some additional structure. And one of that is the spine, this sequence of objects indexed by the natural numbers. And the other is going to be a proxy push-out operation. Now what a proxy push-out does is it extends every span of this form into a commutative square, a specific commutative square, which we're going to call the proxy push-out square. And it's going to obey some conditions. Now there's a condition on the spine saying that every object embeds inside some complete object. And there is the proxy push-out condition, and this is the interesting one. So what we see here is we have a proxy push-out square living inside a larger proxy push-out square. Now if these were actual push-outs, we could get a mediating morphism between them. And what our condition is going to say is that we can still get that for proxy push-outs. So what it's going to say is that there exists a unique mediating morphism that makes diagrams of these form commute. And this axiomatizes the important property that the category of graphs and monomorphisms remembers about the category of graphs and their push-outs. And of course, you can define spine functors. These are just going to be the functors that preserve all the spine category structure. The definition you see here is a bit strict. Some would say it's evil. I use equality of objects pretty freely. Now, you can relax this definition if you care, but it's not all that important, and you'll see why. In any case, we get a bunch of examples. Get the post set of natural numbers, where every element, every natural number, every object belongs to the spine. Everything is complete. And the proxy push-outs are just suprema, are just maxima, are just like regular push-outs. And we will denote this spine category nat, and it will be what we use as the codomain of our abstract Treewidth functor. And another example is, as promised, the category of graphs and monomorphisms. The spine in this case will be the complete graphs on n vertices. And the proxy pushouts are the remembered pushouts. What does this mean? It means that the proxy pushout square in the category of graphs and monomorphisms is just going to be the pushout square in the category of graphs and homomorphisms. And this works similarly for hypergraphs and other structures as well. And now we want to define Treewidth as a spine functor with codomain nat. So we can consider any functor, any spine functor from a category C to nat as some kind of candidate for Treewidth. And we're going to focus our attention on the spine categories for which there is at least one such functor. Right? If there are no such functors, there's no way to obtain a Treewidth for a category. That's the bad case I was talking about earlier. We're going to focus on the good case where there is at least one such functor, and we're going to call it S. But using one such functor S, we can define another functor, delta C, on each category, on each spine category C. And this functor, it will be canonical. Delta C will depend on C only. It will not depend on S. And it will be unique. In particular, it will be maximal. That guarantees uniqueness already. And, as I promised, it will recover Treewidth in the case where C is the category of graphs and monomorphisms. Now, the way this goes is it's interesting. We're first going to define pseudochordal objects. And these are just the objects of our category on which any two spine functors from C to nat give the same answer, give the same number. So all Treewidth candidates, or all Treewidth-like functors, will agree on the pseudochordal objects. And that's the definition of the class of pseudochordal objects. They are precisely these objects on which all Treewidth-like functors agree. One way to define delta C on these objects, it must coincide with S, right? Indeed, it must coincide with the value of any spine functor. We have a spine functor S, so we're just going to define the value of delta C on pseudochordal objects X as S of X. And this works. And once we define the pseudochordal objects, we can use them as sort of test objects to define delta C on any of the other objects. So what we're going to do is we're going to define delta C of X for an arbitrary object X as the infimum of the delta C of all pseudochordal objects which contain X. And this is a valid definition, because delta C has already been defined for pseudochordal objects. So this is fine. And once we do that, well, we're going to call delta C the triangulation functor, and our main result is going to be that delta C is indeed a functor. That's not obvious in the first place. And that it's a spined functor. And finally, that it is the object-wise maximal spined functor. It assigns the highest natural number value possible to the object. And obviously, I won't give you the proof, but it's pretty cool. It involves this cool 3D diagram, so do check it out. It's nice. As I promised, it's actually easy to prove that delta graph M is actually Treewidth. So this looks promising. But more importantly, if we put some very mild computational assumptions on our category C, we even get a uniform algorithm that computes delta C. And you can check this out online here. There's an example where I actually calculate a pretty simple delta functor. Unfortunately, this algorithm is too slow to be practical. It's much slower than the specialized algorithms that you'd use on specific categories to compute Treewidth. But you can technically use it to compute small examples if you have a new category. And the payoff is that once we have that, we even get a sort of abstract analog of 3 decompositions. Now, 3 decompositions are a sort of tree you can recurse on. And this is how you write algorithms for objects of bounded Treewidth in the category of graphs. So this is a pretty standard tool. And turns out we can write algorithms for objects of bounded delta C on an arbitrary spined category C, just like we do algorithms for graphs of bounded Treewidth by recursing on the 3 decomposition. And this is very interesting. We've yet to see whether it is practical, but it's a very good sign that you can do it. It means that our notion of Treewidth is indeed fairly close to the meaning, to the uses of Treewidth that we have in graph theory. Now there's a bit of future work to do here, as you can see. We want to work out more specific examples, and constructing algebraic examples in particular is not all that easy. And finally, as a big picture thing, as a sort of aspiration, well, that's all I wanted to say about Treewidth and spined categories for now. You can check out the paper, you can download the slides. They have a bit of extra content at the end. But for now, I think it's time to hear your feedback and go to your questions. Thank you.
Okay, thanks. This pre-recorded format works quite well. Questions? We have an audience question here.
Hi, thanks for the talk. I was wondering, this data of the spine, is this like a property or a structure? Like, how unique is it? If you choose different graphs, do you get a different kind of property than Treewidth?
So yeah, in some categories, this is structure. In some categories, you can choose the spine rather freely and get different notions. One of the slides contains an example with the lattice of divisibility of n, which is rather free. You can choose the spine in multiple ways. In some other categories, it turns out it doesn't matter. And the category of finite sets is one example. There, it doesn't matter how you choose the spine, as long as it's a spine. You can only get the same. You can only get the same things. In particular, finite sets do not admit any Treewidth-like functor, and that's a proof, no matter which spine you define. So yeah, it's half structure, half property in that sense. In that sometimes it's a property, but most of the time it's an imposed structure. Does that answer the question?
Yeah. So for graphs, if you choose instead of fully connected graphs something else, do you get a different graph property than Treewidth?
Yeah, that's a very good question. If someone figures that out, let me know, and we'll write a paper together. I don't know. There's interesting choices to be made. Like we've proved some things that don't work. Like we know that for planar graphs you can't really choose a spine and things like that. But I don't know if for graphs specifically whether you can choose something else that remains meaningful. It's a good question. Okay.
Thanks.
Okay, there's a couple more questions. Let's take one more question. I think, yeah, Nicholas was first. Sorry.
So sorry.
So there was. I just want to make a quick comment. So there is something in graphs, quasi-topoi, and so on that seems to be the construction you try to emulate. It's called multisums, a la Behr's. So I can send you a reference. So there's something, indeed, it's a case that you don't have enough morphisms if you just quotient on the monos, but there's something called multisum, which allows you still to factorize any jointly surjective cospan through one of the multisum elements. So I'll send you a reference. Maybe this is useful so that you can maybe extend the result to quasi-topoi, which...
Fantastic. Yeah, please,
so,
please do, please do, especially because there's, like, I talked to other people who had similar issues in their categories. So different categories, not graph theoretic categories. So I'd like to know as many.
Yeah, we used this recently for defining actually some sort of notion of composition in quasi-topoi. So maybe that's useful as well. It doesn't seem to be very well known, but it's work by Deers back in the 90s, I think. Yeah, I'll send you a reference.
Fantastic. Thank you. I look forward to it.
Okay. Let's all unmute and thank Zoltan. That's the end of the session.